Hello everyone, my name is Frida Martinez and today I will present our work on the structural and luminescence properties of erbium doped zirconia. Zirconium dioxide, or zirconia, is a material with interesting structural, thermal, and optical properties. In particular, when zirconia is doped with rare earth ions such as erbium, its optical properties can be modified, making it a promising material for photonic and luminescent applications. Erbium ions are especially interesting because they exhibit characteristic electronic transitions that produce luminescence in different regions of the electromagnetic spectrum. Therefore, the main purpose of this work was to investigate how the incorporation of Br3+ ions affects both the crystalline structure and the luminescent properties of zirconia. The main objectives of this research were, first, to characterize the luminescent emission associated with Br3+ ions. Second, to analyze the crystalline structure and phase composition of Br3+ doped zirconia using X-ray diffraction. And finally, to study the excited state dynamics through lifetime measurements and relate these optical properties to the structural characteristics of the material. To accomplish these objectives, we used three main characterization techniques. First, X-ray diffraction. This was used to identify the crystalline phases present in the samples and to observe structural changes associated with erbium incorporation. Second, luminescence spectroscopy. This was used to identify the characteristic emission bands of Br3+ and analyze their behavior. Finally, lifetime measurements. These were performed to study the decay dynamics of the excited states. These measurements provide information about how long the Br3+ ions remain in an excited state before relaxing to a lower energy level. Now, moving on to the main results. The X-ray diffraction measurements showed changes in the crystalline structure of zirconia with the incorporation of Br3+. In particular, we observed a progressive transformation from the monoclinic phase toward the tetragonal phase as the erbium concentration increased. This indicates that the incorporation of Br3+ influences the structural stabilization of zirconia. Regarding the luminescence results, the examples exhibited the characteristic emission bands associated with Br3+ ions. In the green region, we identified transitions from the doublet H11 halves on carded S3 halves excited states to the carded I15 halves ground state. These emissions were among the most relevant features observed in the luminescence spectra. The lifetime analysis provided additional information about the relaxation dynamics of these excited states. Changes in the measured decay times with erbium concentration indicate that the local environment of Br3+ ions and the structural evolution of the zirconia matrix influenced the luminescence response. Together, the X-ray diffraction, emission, and lifetime results show a relationship between the crystalline structure of the material and its optical properties. In conclusion, the incorporation of Br3+ modifies both the structural and luminescent properties of zirconia. X-ray diffraction analysis showed a progressive stabilization of the tetragonal phase with erbium incorporation, while luminescence measurements confirmed the characteristic electronic transitions of Br3+. Lifetime measurements also revealed changes in the excited state dynamics, supporting the relationship between the structural environment of the erbium ions and their optical behavior. Overall, these results highlight the potential of Br3+ doped zirconia as a luminescent material with possible applications in photonic and optical systems. Thank you for your attention.